Hello friends, welcome to my channel. Let's have a look at problem 2492 again. Minimum score of a path between two cities. In this video, we are going to share a solution based on traversal. So we can use breadth first search or depth first search. So in this video, we are going to use depth first search. So first, we'll read through the problem statement, and then we do the analysis, and finally we share the code. First, the statement. We are given a positive integer n representing n cities numbered from 1 to n. We are also given a 2D array rows where rows I equals AI BI distance I indicates that there is a bidirectional road between cities AI and BI with a distance equal to distance I. The cities graph is not necessarily connected, so the score of a path between two cities is defined as the minimum distance of a road in this path. So return the minimum possible score of a path between cities 1 and n. So let's also look at the notes. So first, a path is a sequence of roads between two cities, and secondly, it's allowed for a path to contain the same road multiple times, and we can visit cities 1 and n multiple times along the path. So the test cases are generated such that there is at least one path between 1 and n. So based on the second notes, actually we can interpret that the return should be the minimal road length in the connected component containing cities 1 and n, right? So here let's look at the two examples. So in example 1, the four cities are connected, so we just need to return the minimal road length, that is 5. So similarly in example 2, the return is 2. So with that said, let's look at the constraints. So here we want to point out that the length of or the number of cities is bounded by above by 10 to the power 5, and there are no repeated edges, and there is at least one path between 1 and n. So in other words, so the cities 1 and n are in the same connected component. So with that said, we are ready to do the analysis. So here we are going to use traversal method. Actually, for this problem, we just need to locate the connected component containing cities 1 and n. And then the return is the minimum road distance for rows connecting nodes directly in this connected component. So for finding connected component or components, we typically do union find or traversal, such as breadth first search or depth first search. In the previous video, we have demonstrated how to use union find, and in this video, we're going to use a traversal. Here we choose to use depth first search. So with that said, we can do the code step by step. So first, I'm going to build the graph. So this is a very routine. So notice that the graph here is a bidirectional graph. So let's do this, collections, default, dict. So I'm going to use the container dictionary, right? Then we are going to iterate for I, J, and D in rows. So what we are going to do is graph I, which is a dictionary. So I'm going to the neighbor J has distance D, graph G I also equals D. So this way we finished building the graph. So second step is to get connected components. Component containing 1 and n. So for this, I will first write a hyperfunction to make the code modularized. So let's write a function that's called connected components. Get connect component. So we are going to have a starting node. Let's call it I. So we are going to call this component visited. This is what we want to return. So here I'm going to use this S as a stack to correspond to depth first search. If you use this one as a deck, as a queue, this will correspond to a breadth first search. So with that said, let's do a while loop, while S. So first we want to get the node, that is s_pop. Then we are going to add this guy to visited, right? Add this node, and then we want to check its neighbors. So for neighbor and distance in graph node. So notice that graph node is a dictionary. So we want to do the items, right? So if neighbor not in, so actually we do not need to pay attention to D here. So let me write it like this. For neighbor not in, or we even simplify the graph. So let's write like this. For neighbor not in visited, so we can add this one, append this one to the queue, and then this is a standard getting connected component method, right? So we're going to return the visited. So this after this preparation, so we can write the problem logic. So for the problem logic, it's also very simple. So let's call this get connected component, right? So by the problem assumption, so cities 1 and n are in the same connected component. I just need to call like this, and then we are going to initialize a result. Let's call it float infinity, right? And then we are going to iterate I, j, and d in rows. Then we want to check if I in this set and j in this set. If so, we are going to update the result, right? So not maximum, as a minimum of the result, and d, right? So we just need to return the result state now. So this forms a solution format, right? So now let's do a check first. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the generic cases. So here, actually, because of the way we're doing the code, here actually we can slightly save some space. So here actually we can use the set, right? So we just do this. Graph I add G. Graph G add I. So in other words, at first we don't pay attention to the distance. So here for neighbor, so we want to change this for neighbor in graph nodes. So here is a set, right? So here nothing changes. So nothing changes, right? So let's test this code also. Yeah, this passes a special example. Now let's look at the generic case. Yeah, it passes all the generic cases. So I would say this code for sure can be further improved, but we want to use this code to fix the idea. So with that said, that's about it for this specific problem. So in this video, we shared the idea of locating connected components using traversal. We can either use BFS or DFS. Then we connect this method with the problem logic to finish the problem solution. With that said, I guess that's about it for this video. Thank you.